So viscosity. So in a qualitative manner, I have told you that viscosity is resistance to flow. So viscosity is a characteristic, a property of all fluids. Fluids means the substances which can flow, the liquids and the gases. And it is defined as the property by virtue of which it tends to oppose the relative motion between two adjacent layers of the fluid. Suppose if you cannot understand, simply look at the diagram which is given at the bottom. Let this be a layer. See, water is flowing through a pipe, means water flows in infinite layers. If a gas flows in a pipe, gas flows in infinite layers. Now this one layer is moving and another layer is moving, and because of these two layers moving in different velocities, one layer drags the flow of the other layer. This is how the resistance to flow is developed. So one layer drags the flow of the other layer, so which is originated due to the internal friction among the layers. It is because of the internal friction existing between the molecules of the gas or the liquid. So in the case of liquids, this internal friction is arising due to the cohesive force, because in the case of liquids, the liquid molecules are very close to each other because of the cohesion. The cohesion arises due to the intermolecular attraction. Suppose if you take water molecules are connected to one another by hydrogen bond. Therefore, if you pull one water molecule, that water molecule will attract the other water molecule. Therefore, there is a dragging, a continuous dragging, where the force is transferred from one molecule to the other molecule because of the cohesion. But in the case of gaseous molecules, we have already assumed that the gaseous molecules do not have intermolecular interactions. That is ideal gases. There is a transfer of a momentum which arises due to the collision. There is a transfer of a momentum between the layers, and that force, look here, that force per unit area required to establish a unit velocity gradient between the two adjacent layers of a fluid, which are separated by a unit distance. Look at the diagram once again. This particular part you should thoroughly understand. See, this is a layer and this is another layer. The first layer is moving with a velocity, let me say this is moving with a velocity x plus 1 meter per second. And the other layer has to move with a velocity x meter per second. That is 1 unit less. This is what is mentioned as unit velocity gradient. That means the velocity difference between this layer and this layer is 1 unit, that is 1 meter per second. When these two layers are separated by a distance of unit, that is 1 meter. In such a case, what might be the force required to cause this gradient difference per unit area? It is called the viscosity force. That is the force force acting per unit area which is required to make the gradient, unit velocity gradient between the layers separated by a unit distance, and the negative sign is due to this force is used to decrease the velocity by unity. So force is equal to minus eta dou Vy by dou Z. Vy is the velocity along y direction. So the layers are along Z direction. So this is y direction, this is Z direction. So the layers are arranged in the Z direction, whereas movement is observed in the y direction. So there is a change in the Vy with a change in the dz, and it is caused by a force. That force is actually opposite sign, which means the velocity decreases, and eta is the proportionality constant. So F is equal to minus eta dVy by dz, where eta is called coefficient of viscosity. Now look here. So the negative sign, the explanation is given in the, for the negative sign, velocity decreases in the successive layers. So say first layer x meter per second, second layer x minus 1 meter per second, third layer x minus 2 meter per second. Therefore, the difference between the velocity with z, the other scale. So this is y direction, this is z direction. So dVy, that is change of velocity along y, with change in layer in the z direction is a negative. Now look here, force, this is the force, which means we are, what the force we are acting, actually we are discussing for the decrease in the velocity in the multi-layers. This force is acting per unit area. What is force? Kilogram meter per second square. How did we get this unit? Force is equal to mass times acceleration. You should always remember this. Force is equal to mass times acceleration. So mass kilogram, what is acceleration? It is rate of change of velocity. What is velocity? Meter per second. What is velocity? Rate of change of displacement. Therefore, it is meter per second square divided by meter square. That is force acting per unit area. Listen here, this is not a pressure. Actually, pressure is also the same, force per unit area. But here we are discussing it in a different dimension. So kilogram meter per second square divided by meter square. So dVy by dx is equal to, look here, this is dx or dz is also presented as meter. The change in velocity is presented as meter per second. So for eta, if you multiply, see, F into dz by dvx, just the inverse you have to take. Look here. You want to find out the unit for eta. So F is here. So this particular part will go there as an inverse. So that is what is taken here. M is in the numerator, meter per second is in the denominator. But here meter per second is in the numerator, meter in the denominator. Why it is taken like this? It is F into the inverse. That is, we are going to derive the unit for eta. So kilogram meter per second square divided by meter square, that is what is this, force per unit area, into inverse of this, that is meter per second. So when you simplify this, you are getting kilogram per meter per second, which is the unit for eta, which is viscosity coefficient. Actually, in CGS system, it is given the unit poise. Poise means 0.1 kilogram per meter per second. But actually, this 0.1 kilogram per meter per second is a very big quantity. Very big quantity. Therefore, for gases, the coefficient of viscosity is given in the units micropoise, where 1 micropoise is called 10 power minus 3 kilogram meter per second. For liquids, it is given as a centipoise. Actually, book it is 10 power minus 7, it is given. I think it is wrong. Let me check that and tell you again. It is expressed in centipoise. 1 kilogram per meter per second is equal to 1 Pascal second. 1 Pascal second. So this is the importance of the unit of the viscosity coefficient. Now look here. I have already told you, in the case of liquid substances, the resistance developed between the layers of liquid is due to the intermolecular forces. You should imagine actually what I am telling you. If it is a direct class, I would have explained much better. Just to close your eyes and try to visualize. Suppose in a river, the water is flowing. You can see at the center of the river, water flows with high speed. But when you move away from the center to the banks, in the banks, the velocity of the water is less. But at the center, the velocity of water is high. That one stream coming with a high velocity, it drags the neighboring stream. That dragging is due to the intermolecular forces. Or I can say the water which is close to the bank is with low velocity, which tries to retard the other water which goes with the higher velocity. This is also because of the resistance developed by the adjacent layers. And this resistance is also due to intermolecular forces. But in the case of gases, as the gases do not have intermolecular forces, this resistance developed between the layers is due to the transfer of the momentum. You know what is momentum? Momentum is a mass times velocity. So because of the intermolecular collisions, the momentum of a particular gas atom which moves faster is colliding with another gas molecule which moves with a slower rate, and there is an exchange of the momentum. And because of that, the molecule moving with lower momentum will now start moving with a higher momentum. At the same time, the gas molecule which was earlier moving with a faster rate will now move with a slower rate. So this is called viscous drag. Some velocity, the same, they are trying to put all molecules in the same velocity in all layers. And this is happening because of the transfer of the momentum. So how the momentum is transferred from one molecule to the other molecule? The transfer is caused by the collision, or the collision is making the transfer of momentum. Now, the rate of transfer momentum, how fast the momentum is transferred. The rate of momentum transfer is proportional to the average velocity and the mean free path of the atom. So the gas molecules are moving with an average velocity, and also they are moving with a mean free path, and these are the two factors which affect the rate of momentum transfer. So the rate of momentum transfer is depending upon the average velocity and the free mean path, mean free path. So you can relate all these things together and you can write an equation. The eta, the coefficient of viscosity, is equal to 1 by 3 lambda. What is lambda? Lambda is mean free path into the average velocity into the mass of the molecule into the number density of the gas, number density. and rho is number density. The number density is n, number of molecules by volume, which can be written as P by kT. P by kT. This derivation we have already seen. And you know the equation for lambda. Lambda is kT divided by root 2 pi sigma square P. You know what is sigma? Sigma is collision cross section. Their average velocity also, you know, it is square root of 8 kT divided by pi m. So when you substitute these values in this equation, you are getting eta is equal to 1 by 3 kT divided by root 2 pi sigma square P into 8 kT by pi m whole power half. So these two things over. Then comes mass of the gas. Then comes rho, where rho is P by kT. So rho is P by kT. So after the simplification of the entire thing, you are getting eta is equal to 2 m, that is molar mass, RT whole power half divided by 3 pi 3 by 2 Avogadro number Na sigma square. You may wonder how here comes a 2. Actually, the 2 comes here. This 8 can be taken as 4 into 2. If it is 4 multiplied by 2, taking the square root, 4 square root 2 comes out. Another root 2 is there. That root 2 and this root 2 will get cancelled. And you may wonder how this molecular weight has come. The molecular weight actually has come like this. Molecular weight by Avogadro number, or Avogadro number by molecular weight, is the mass of the substance. Actually, this mass is replaced by molecular weight. And also, this K is replaced by R. The K is replaced by R. So many Ks are there, no? Here is one K, root K. Here is another K. Here is another K. So finally, we are getting a R here because Nk is equal to R. That is how this R has come here. That is how this molar mass has come here. So molar mass and Avogadro number are introduced in the place of mass and Boltzmann's constant. So if you carefully do each substitution, you yourself can arrive at this expression. So eta is equal to 2 molar mass RT whole power half divided by 3 pi 3 by 2. Why 3 by 2? Here is a pi power half here and here is a pi power 1 here. If you sum it up, you are getting pi 3 by 2 Avogadro number sigma square. This is how the equation has come. So look here, looking at the equation, eta is independent of pressure because eta changes only with rho. Eta changes with rho, with mass, with average velocity, with mean free path. It is independent of pressure. Directly it is independent, but indirectly it is dependent because when P changes, average velocity changes, lambda changes, and rho also changes. But when you look at the equation, eta is independent of the pressure. This is called Chapman's equation. Now, how to relate the mean free path with eta? Look here, lambda, the mean free path, is equal to, from this equation, take the lambda out, you can take this 2 here and Cm rho down. Therefore, you are getting lambda is equal to 2 eta divided by average velocity, mass of the gas into number density. So this is equal to this mass and the number density when they are multiplied together. See, I am having say 10 molecules. I am taking the mass. When you multiply 10 molecules per unit volume into mass of a molecule, you are getting simply the mass per unit volume, which I can say as rho dash, which is the density of the gas, normal density of the gas. Whereas rho is called number density of the gas. If the number density is multiplied by mass, you are getting near the density of the gas, that is mass of gas by volume of the gas. So you are getting lambda is equal to 2 eta average velocity into rho dash, where rho dash is simply the density of the gas. Look here, molar volume into P is equal to RT, which is ideal gas equation. And you can write molar volume is equal to RT by P. What is rho dash? Rho dash is simply the density of the gas, which is molar mass divided by molar volume. So molar volume you have got here RT by P. So when you substitute the RT by P here, you are getting rho dash is equal to P into molar mass divided by RT. Let me say this is equation A. And you know what is C? It is 8 RT by pi molar mass whole power half. I am substituting these two values in the given expression for lambda. You are getting lambda is equal to 1 by root 2 P into pi RT by molar mass whole power half into eta. So this is the relation between mean free path and the coefficient of viscosity. If you know this equation, you can very easily find out the relation between mean free path and the coefficient of viscosity. This is a very important thing. Another thing, see, lambda is equal to kt by root 2 into p pi sigma square, where sigma is the collision diameter. So from this, lambda is equal to 1 by root 2 p pi RT divided by whole power half eta. This is our previously derived equation. This is this equation. This is this equation. This is what we have seen in the gaseous state equation. So I am equating these two. Both are equal. So this is the lambda we got from the gaseous state using the collision cross section. This is what we have derived from the eta. Now these two are equal. Therefore, I am equating them and I am replacing the Boltzmann's constant with the gas constant and I am calculating sigma square. This is sigma square is equal to RT whole power half divided by pi 3 by 2 Na eta. This is the relation between eta and the collision cross section. So eta and mean free path can be related. Eta and the collision cross section can be related. So now the next discussion is why eta is independent of pressure. See, more molecules are found at high pressure, but that reduces mean free path. So when, see, look at the relation mean free path and pressure are inversely related. Mean free path and eta are directly related. So more, in one sense, it increases the number density. In another sense, it reduces the mean free path. So one factor is increasing the eta, the other factor is decreasing the eta. Therefore, actually the pressure is not making any change in the eta. That is what is the understanding. And also, this eta is directly proportional to square root of temperature. That means what? At high temperature, there is a momentum transportation. Momentum is changing from one molecule to the other molecule due to the collision which takes place at a higher temperature. But in the case of liquids, what happens? Eta decreases with the rise in temperature. See, in the case of gases, eta increases with increase in temperature. But for liquids, eta decreases with increase in temperature. It is because viscosity of the liquids are found to be dominated by the intermolecular forces. These intermolecular forces are broken when the temperature is raised. But in the case of gases, the Viscosity is controlled by the collision, where the collision increases by increase in temperature. Therefore, at a high temperature, intermolecular forces break and the liquids become more fluidity. But gases, the fluidity is controlled by the collision. So you should understand the difference between the liquid and the gases in things pertaining to viscosity. See, in the lower classes, you might have studied the very small differences among the solids, liquids, and gases. But see, the same thing, and we are looking in a more mathematical manner and also more philosophical approach. What happens to the fluidity of the liquids when temperature is raised? When you raise the temperature, the intermolecular forces which connect the liquid molecules, they vanish. And because of that, the liquids assume more fluidity at higher temperatures. But in the case of gases, there is enormous amount of momentum transfer from one molecule to the other molecule at higher temperatures because of the high kinetic energy and the less free mean free path and also more collision. So the gas molecules, they are controlled by the collision, but the liquid molecules are dominated by the intermolecular forces. So these are the very important understandings. So with this, we are, I think, a few more discussions are there in the gaseous state, which we will be discussing a little bit later.